In object pose estimation, we are given a 2D image depicting a vehicle, depicting an object, and also the 3D CAD model of this object. Our goal is to detect the object in this 2D image and also to estimate its 3D rotation and translation with respect to the camera. In object pose estimation, the famous two-stage pipeline works as follows. In the first stage, we train a neural network to detect 2D semantic key points in this image, such as shown here. In practice, this neural network can often make mistakes and generate a set of wrong matches that we call outliers. And then in the second stage, given these correspondences, our goal is to estimate the 3D rotation and translation. A well-known heuristic algorithm in this stage is called RANSAG, which stands for Random Sampling Consensus. So what can possibly go wrong with this two-stage pipeline? We argue that there are three challenges associated with this pipeline. The first challenge is that RANSAG and similar algorithms can fail without giving any notice. The second challenge is that these key points can be arbitrarily wrong. And the third challenge is that there is no provably correct pose uncertainty coming from these pose estimation pipeline. Although related work has proposed certifiable algorithms to address the first challenge, in this paper we seek to address the second and third challenges. Specifically, we designed the first pose estimation pipeline with statistical guarantees. In the first stage, we designed what we call the conformal keypoint detection approach, where instead of outputting single point estimations for each of the key points, we output a set estimation for a single key point, shown as this 2D yellow ball in this image. We draw one ball for each key point, and with this set of 2D balls, what we can guarantee is that this set of balls, they cover the ground truth key points with the user-specified probability. And then in the second stage, we propagate the uncertainty on the key points to the 6D pose, forming what we call the pose uncertainty set, or PURSE in short. Here we show the boundary of the PURSE plotted in 3D Euler angles and translations. Similarly, similar to the 2D yellow balls, what we can guarantee is that the ground truth pose lies in this PURSE with the user-specified probability guarantee. Now we can tell you a little bit details about how we have designed the two stages. In the first stage, let's talk about conformal keypoint detection. In conformal keypoint detection, we are given a 2D RGB image, and our goal is to predict a set of semantic key points. Let's call YK the case semantic key point. Suppose we trained a neural network that can detect this 2D semantic key point. Specifically, we chose the neural network that can output a heat map of this of location of YK, shown in this transparent image here. Let's call FK of X the case heat map. So the first thing we do in conformal keypoint detection is to design what we call a nonconformity function. If the neural network performs very badly on this keypoint prediction task, then the nonconformity function will evaluate to a very large value. Specifically, we design the nonconformity function as follows. We first design a function phi that takes in the ground truth location of the case key point yk and the case heat map, which is fk of x. Let's call pk the maximum probability in this heat map, and qk the location where the maximum probability is attained. We compute phi by evaluating the distance from q star to the ground truth key point yk, and then we pre-multiply this distance with the maximum probability pk. We then take the nonconformity function to be the maximum of all these key point level function phi's. And then with this nonconformity function R, what we can do is we can calibrate this nonconformity function on a set of images that we have not seen during training. This calibration procedure will lead to a set of n scores that we call alpha of pi 1 up to pi n, which we've sorted from the largest to the smallest. So now, after the calibration procedure, the user comes in and gives us an expected error rate, epsilon. With this epsilon, we compute the 1 minus epsilon quantile of this set of scores that we simply call it alpha. And then at test time, given a new image xl of xl plus 1, we output all the set of labels such that the nonconformity score is below alpha. Mathematically, this becomes a set of mathematically, the set of key points becomes a set of 2D balls that are centered at the heat map center with the radius that is inversely proportional to the maximum probability, and the radius is also proportional to the quantile alpha. In the second stage, we propagate the uncertainty on the key points to the 60 poles. In geometric uncertainty propagation, we are inspired by the machinery called set membership estimation in control theory. And what we do is that we simply rewrite the constraint on the key points to become constraints on the 60 poles. We do this by noting that the case key point yk is nothing but the reprojection of the 3D key point after Richard transformation of the ground truth poles R and T. Let's call S the concatenation of the ground truth rotation and translation. We can write this constraint now as a quadratic and linear constraints on the ground truth poles S. This gives us the poles uncertainty set, which is nothing but an abstract mathematical subset of SC3 that is governed by a set of quadratic and linear constraints. We call this the poles uncertainty set, and this picture plots the boundary of this purse in 3D rotation and translation. With this purse, we can do several things. The first thing we can do is that we can check membership. Given any pose estimation, we can check if this pose estimation is in fact in the purse. This boils down to just evaluating the quadratic and linear constraints at the pose estimation. We can also generate samples and average from these samples. We propose an algorithm called random sample averaging that is inspired by the well-known RANSAG algorithm. We can also compute a worst-case error bound from any pose estimation to the ground truth pose. This is done by formulating the optimization problem that computes the maximum distance from any pose estimator to the purse set. Intuitively, the maximum distance from the pose estimation to the purse set gives us an upper bound of the distance from the pose estimation to the ground truth pose. This is a nonconvex optimization problem, and we show that we can use convex semidefinite relaxations to solve them to exact global optimality. We perform experiments on the LineMOD Occlusion dataset where we calibrate on 200 images and test on 1,214 images. We test two expected error rates, epsilon equal to 10% and 40%. This here we show that the purse does empirically contain the ground truth pose. Here we show that when the expected error rate is 10%, the purse empirically covers the ground truth at roughly 90%, and when the expected error rate is 40%, the empirical coverage is around 60%. Here we show that we can compute the reasonable error bounds with respect to the ground truth pose. In this plot, the y-axis is the rotation error bound, and the y-axis is the actual rotation error between the average pose and the ground truth pose. We see that our bounds are always larger than the actual error, which means that our bounds are always correct. And we also see that when in most of the test cases, our bounds are actually reasonably close to the actual error, but we do notice that in some cases our bounds can be overly conservative. When the expected error rate is about 40%, the bounds become much tighter than the case when the expected error rate is 10%. So we also show, lastly, we also show that we obtain these statistical guarantees without sacrificing much on the empirical performance. Compared to a set of state-of-the-art baselines, we see that our average pose estimation are actually much, in most cases, better than these state-of-the-art baselines. To conclude, we've designed the first object pose estimation pipeline with statistical guarantees, where in the first stage we use conformal key point detection to output prediction sets that guarantee statistical coverage of the ground truth key points. And then in the second stage, we use geometric uncertainty propagation to formulate pose uncertainty sets from which we can sample and also compute worst-case error bounds. For more technical details, please visit our poster on Wednesday morning with number 69. Thank you.